Chapter 8, Section 2. We will also cover Section 3 today. Section 2 is measuring earthquakes. The first thing that you need to know before we can measure earthquakes are what earthquake waves are. So we have two things, seismographs, which are the instruments that record the earthquake waves, which is what you see here. And then we have seismograms, which is the trace or the actual image that you have that's recorded. And that's what you see here. So surface waves, those are the seismic waves that travel along Earth's very outer layer, so along the surface of the Earth. And then we have body waves. These are the ones that go through the interior of the Earth. So we have P waves, those that push and pull or compress and expand. So P waves are actually longitudinal waves in the direction that waves travel. They can travel through solids, liquids, and gases. And then we have, they have the greatest velocity out of all earthquake waves, out of the P waves, out of the surface waves, and then of course out of the S waves. These travel along Earth's outer layer, so these cannot go through the core. That means they can only go through a liquid material. They cannot go through solids. They will shake at right angles, so these are transverse waves. And again, they travel only through solids, and they are slower than P waves. So as we're measuring seismic waves, the first ones that are going to hit are going to be your P waves. And you can see how those affect at the very top up here. They're expanding and compressing, so it's moving things back and forth along the land. Then we have, of course, the S waves. It's kind of the up and down motion. And then these surface waves are moving back and forth or up and down. So how we locate earthquakes, you need direction. So we look at travel time graphs from 3 or more seismograph stations. And you can use those 3 or more stations to find the exact location of an earthquake epicenter. So for example, if we have an earthquake, and let's say that this is our travel time, this is our graph. So we have the P wave, you have a time that it hits, and then you have a time that the S wave hits. All right. The travel time is 5 minutes, and you also have a distance when those hit. All right. So based on how long it takes, then you can calculate the distance. So this is about 3,900 kilometers. So if you look here, when we graph that from a central point, so let's say from Montreal, it was 5,500 kilometers. From Paris, it was 6,700. All right, and then from Sao Paulo, we have another number. Where those 3 intersect is your epicenter. You have to have at least 3 or more. Now, earthquake zones. About 95% of the major earthquakes occur in just a few narrow places. So think about the Ring of Fire. And sizing earthquakes, we have to use 2 things, intensity and magnitude. So we have the Richter scale for our magnitude. This is based on your amplitude of the largest seismic wave, so that could be a body wave or a surface wave. And each Richter scale magnitude equates to a 32-fold energy increase. So that means it's multiplying itself 32 times. So the bad thing is that the Richter scale does not adequately estimate really big earthquakes. However, moment magnitude, or intensity, does. So the amount of displacement that occurs along a fault zone. So this is much more accurate, and this is much more widely used, and it estimates your energy released. This does measure very large earthquakes. So magnitudes, if it's less than a 2.0, it's generally not felt, but it can be recorded. 4.0 to 4.9 can be strongly felt. 7.0 to 7.9, these are your major earthquakes. They inflict serious damage. And an 8.0 or above, these will destroy communities that are near the epicenter. And you can see the estimated number per year. So with less than a 2.0, we actually have over 600,000 earthquakes a year that usually are not felt. 12 that are major earthquakes, and usually 0 or maybe 1 in a year that will be an 8.0 or above. So these are some notable earthquakes, and this is in your textbook, so I just want to glance through this. Which the greatest one that's on this list is from Tokyo, Japan in 1923. There were 143,000 deaths. It was a 7.9. However, the largest that's on this scale is a 9.6, and that was from southern Chile in 1960. Now, why were there more deaths in Tokyo, Japan than southern Chile, even though the one in southern Chile was a much larger earthquake? Think about that, and I want you to write that in your notes and circle it. All right, 8.3, destruction from earthquakes. We have seismic vibrations. So damage to buildings and other structures depend on 3 things: intensity and duration of vibration, nature of the material the structure is built on, and the design of the structure. So your building design, structural damage can be affected by the intensity of the earthquake. If you have unreinforced stone or brick buildings, those are serious safety threats. So steel is a much better type of structure, and the material your structure is built on determines how much structure damage you have. And again, also the design. We also have a term called liquefaction. It's a saturated material that you have that turns into a fluid. So let's say that you have a really moist type of ground and an earthquake occurs. All of that water is going to get moved that's in that material and is going to become kind of like a miniature lake of quicksand. So it's going to start moving things. Anything that's underground may start to float to the surface. And if you have a building that's on this, it may actually start to sink. So here's a great example. Tsunamis. These are triggered by earthquakes. So when you have an earthquake that's out in the ocean, so the ocean floor is actually displaced vertically along a fault, and that triggers a tsunami. It can occur when you have a vibration of a quake that sets off an underwater landslide. And tsunami is Japanese for seismic sea wave. And you can see how that happens here. We do have a tsunami warning system. Large earthquakes are actually reported to Hawaii from the Pacific seismic stations. And Hawaii will actually, they have a station there where they can actually tell when the water level drops to a great extent, and that means there's usually a tsunami. So even though they travel quickly, there's usually sufficient time to get an evacuation warning out there. Other dangers, we have landslides from earthquakes, so structures or sinking of ground. We also have fires that can occur. In San Francisco in 1906, the most destruction was caused by a fire that started when gas and electrical lines were cut and began to explode for that earthquake. Predictions, short-range predictions, have not really been successful just because we aren't sure what is a foreshock and what is an aftershock for an earthquake. However, long-range forecasts are more accurate, even though we really don't understand how or where the earthquakes are going to occur. We just know that they will at some point. We also have what's known as a seismic gap. That's an area along a fault where there has not been any earthquake activity for a long period of time. So today, read 8.2 and 8.3 in your Earth Science book, do the 8.2 and 8.3 handout, and that will be it for today.